Good morning. Hi, everybody. Welcome to the last lecture of 512 and also the last lecture of the block, I guess, right? Yeah. Good job. Okay. So today's lecture is kind of continuing on the theme that we have started with in the previous lecture, the theme of optimization. But in this lecture, we're going to be looking at a different class of problems that we are going to be able to solve more efficiently by using an algorithm called, it's a specific way of looking at a problem called dynamic programming. So in the previous lecture, we had linear programming, which was a way of solving optimization problems when we were dealing with a problem in which we had linear constraints and linear objectives. That was a separate class, and I told you that there's another class of optimization problems, nonlinear problems, which we'll look into in other courses in MDS. And in this lecture, we're going to be dealing with this particular type of problems, which we're going to be able to solve using dynamic programming. But before that, we're going to get started with something called caching in programming in general, and that's an ingredient that we will need for the subsequent discussions in this lecture. So let's get started with that. Okay. All right. So we've discussed the Fibonacci sequence early in the course, and the way that we looked at that was by saying that, okay, this is a sequence in which each term is dependent on the previous terms, and I used that as an example to introduce you to recursive algorithms, an algorithm that's kind of defined in terms of itself. But there was one problem with the Fibonacci sequence and the way that we computed it using a recursive algorithm in Python, and that was the fact that, what was the problem with that? Sure, yeah. So the problem basically was that it was too slow because we had to redo a bunch of computations. And here I'm going to show you a demonstration of this. So this was our original implementation. So a recursive function here, recursive call here, another recursive call here, meaning that we will have a time complexity of 2 to the power of n. And if we can obviously compute small values for the Fibonacci sequence, but for larger values, we will run into a problem. However, I have a different implementation here. It looks the same, but slightly different. It's implemented using basically a NumPy array. Just let's look at the results first and then discuss what it does. So it does exactly the same thing, but in a different way. It's exactly the same thing, done in a different way. So let me just time the two. This one is the recursive one. Okay. All right, 3.24 seconds, and this one is using the NumPy array thing, and it was just instantaneous. Okay, so the problem is that, just like you mentioned, the problem is that we do a bunch of repetitive computations when we implement it recursively. For example, if we want to, for example, compute Fibonacci sequence of 35, we're going to need a function called to like 34 and 33, and inside of like 34, we're going to again call 33, and then we're going to do the whole bunch of repetitive operations over and over again. However, with the array approach that we have seen here, we don't redo computations. We simply start from the smallest value and basically progress towards the solution that we want. So in this way, each value is going to be computed only once, and we don't do a whole bunch of repetitive computations. All right. So we encountered the same kind of problem when we talked about graphs. For example, if we have a graph like this here, so node A over here, let me magnify, okay. If node A is over here and we have a giant graph in between and then node B, and suppose that we want to compute the distance between node A and node B, for example, okay, we do a bunch of computations, we arrive at the distance, and then suppose that we also need to compute the distance from node A to node C. Then we have to redo all the computations again if we are not, if we don't implement it in a clever way to save computations. So again, the same kind of theme of problem happening here as well. Okay, so with recursive calls, with this graph thing, we have to be careful to kind of save the intermediate results in a way in order to avoid repetitive computations. All right. So the way that we can address this, just like I showed you, is by using a concept called caching, or another term for it is memoization. So what I showed you at the top by storing intermediate results in an array, this is an example of caching the intermediate results so that we don't have to recompute things over and over again. And we can do this directly without changing this recursive code over here, and I'll show you how we can do that. So memoization, this term, is different from memorization, but it's kind of doing the same thing. It's used in computer science lingo to refer to the fact that when we make a call to a function with a specific argument, we're going to save the results of that specific call to that function. So if you call Fibonacci of 5, for example, and that gives us a result, we're going to save that in a data structure somewhere in order to cache that result. It's basically the same kind of thing when you're surfing the internet. Then if you visit a page multiple times, the browser is smart enough not to reload the entire page every time, and thereby saving a lot of your time and saving some network traffic as well. It's basically the same thing. Okay, and you have seen this a lot when you want to clear your browser cache and something like that, so it comes up, the term comes up there as well. Okay, so let's see how we can turn this recursive call into a memoized version of that. And in Python, that's pretty easy. Okay, so there is this LRU cache decorator, which is part of base Python, and it's basically used as a decorator. So right above the function that you want to cache, you want to tell Python, hey, save the intermediate calls to these functions so that I don't have to recompute them. You can just decorate that function with this @functools LRU cache, and then it does exactly that for you. Okay, let's run this and see if it really works. There we go. So it's the same recursive function, but now Python knows, okay, every time a new call is made to that function, I'm going to save the results. Okay, how can we implement that ourselves? In particular, what specific data structure can we use to implement this functionality? Exactly, yeah, a dictionary is what I would use because we have arguments, and we have arguments put into that function and then return values. Pardon me? A set, then we can't have key value pairs, and then we don't know what argument caused that function to return that particular value. So yeah, we can do it using a dictionary ourselves, but here it's implemented already for us in Python. Okay. Questions? No, not exactly. That's an example of dynamic programming. But in dynamic programming, we usually use memoization to save intermediate results. That's how these two are related. Yeah, but we'll get to that. Yes. Oh, okay. So you mean if we cache the values here and then we restart the kernel, then with another call we have to recompute all of those. So yeah, actually I have a piece of snippet of code here that gives you the possibility to save actually the cache. So that's the piece of code here, just in case if you want to refer back to this notebook later on, if you really need that. Yeah, you can save it to the hard drive and then load it again and use it to to recompute their values. Yeah. Yeah. Even if this wasn't available, you could have created a dictionary, and there is a Python library called, I guess, Pickle, which you can use to save binary objects from Python right to the hard disk, and then reload it back again and use that. Yeah. Okay. And let me see. We have also this. Okay, yeah, this was all I wanted to tell you. Again, basically, this does the same thing, just as I said. It just saves the caching results to the hard drive so that you can use it later on without making that cache data structure all over again. Okay, questions before moving on to the next section? All right. All right, so for the next part, we're gonna be focusing mostly on the lab problem, so the seam carving problem. I hope that by now you have at least looked at the lab to kind of get an idea what this is about, but I'm going to give you a really quick summary of what's happening there. So let me pull up the lab notebook. All right. Okay, quick overview. So we all have resized an image probably more than once in the past, and we know that when we resize an image, if we do the resizing along a particular direction, we're going to have some scaling effects, basically. So objects get compressed or get widened, weird effects happening like that, which is not desirable. However, seam carving is a technique to basically avoid that scaling of objects by implementing a really smart way of resizing images. And how it does that is that, so it says that there are some pixels in an image. For example, if we want to scale this image along the width direction, there are some pixels in their vertical path that if we remove them, it will probably go unnoticed. So we can just remove that particular path, and then the image gets a little bit smaller, and then we can remove another path again, and the image gets a little bit smaller, and then in that way we haven't touched the important parts of the image, okay? And it really works very nicely. I have linked to a YouTube video in the lab. It's like 5 minutes or so. I highly recommend you watching that. It's a nice demonstration. And I'll also show you an example of this, an interactive example of this in the lab. But that's basically the idea. So how does it really tell how we can choose that particular path or that particular seam, so to speak? It uses the concept of energy, and the energy, the way that it's defined in image processing is nothing but saying that, hey, the rate of changes around this particular pixel is so small, so there's probably nothing happening. There's not a lot of change around that pixel, so I'm going to remove that. Because when they're like an object in the background and there's difference between the color here, it means that something is going on. So if you remove those pixels, we probably are removing something really important. That's the whole idea behind it. So we compute the energies for the entire path, and then we are interested in a path that has the minimum amount of energy or the minimum amount of differences around those pixels. And we just take it out. And then we do it again, take it out. So the whole idea here is that it's an optimization problem, right? We're looking for a path among all possible paths that gives us a minimum value for the energy function. Questions about that? Okay. It's the immediate adjacent pixels. So the question is, what is the energy? Does it use the immediately adjacent pixels? Yes, it uses basically derivative in this direction or in this direction. And for that derivative, to construct that derivative, you can use finite differences. And usually it just takes the 2 pixels right around that target pixel. You can use higher order schemes, but in this case, it's okay. Any other questions? Okay. All right. So in this lab, you work on this problem and you come up with solutions to optimize this energy function and find the path that has minimum amount of energy in it, so that if you remove it, it's really very unimportant. And you do it in 4 different ways. One way just uses the linear programming idea that we talked about in the previous lecture. The other one just uses brute force. Another one uses dynamic programming. And finally, you vectorize your code. Okay, so that's basically the theme of the lab. So now we're ready to jump into the topic of dynamic programming. All right, before getting started with this, let me begin with an example. So suppose that we want to get from Vancouver to Quebec City, and then we want to have a stop in Montreal. Okay. In that case, suppose that we can take a flight, we can drive in both paths, we can also take a bike or walk there, although it's crazy. So we have all of these options available, and each one of these options takes a certain amount of time. Okay, and we want to find the choice of the different methods that we can get from Vancouver to Montreal and Montreal to Quebec City, so that the travel time is minimized. Okay, so what would be the brute force way to approach this problem? Exactly. Try all of these paths. So take a plane from Vancouver to Montreal, take a plane from Montreal to Quebec City, compute the time. Take a train from here to Montreal, and then take a flight from Montreal to Quebec City, compute the time. And then once you have been through all of these options, then compute the minimum value and the corresponding travel plan. That would be the brute force way. But it's kind of, it would be really stupid to do that. You agree? Right? Because we kind of have some prior knowledge about the things that are happening in there. In this particular problem, it's very easy to see what's wrong. We don't want to consider all the options. So in the previous lecture, we talked about problems that there is, again, some knowledge about the structure of the problem, some prior knowledge that helps us eliminate a lot of possible solutions in advance without looking at them. Okay? So suppose that one possible solution is that I do some form of travel from Vancouver to Montreal, and then I know that from Montreal to Quebec City, I want to, let's say, ride a bicycle. Is it really necessary to consider all other possibilities from Vancouver to Montreal? No, because at the end of the day, we're going to ride a bike from Montreal to Quebec City, and that ruins the whole thing. Okay. All right. So this is the kind of problem that if we want to optimize the entire thing, the entire travel time, we can actually start optimizing the sub-problems. Okay, so if we optimize our travel time from Vancouver to Montreal and then from Montreal to Quebec City, this will optimize the entire problem. Do you agree? Yeah, okay. So this is when the idea of dynamic programming comes into play. So dynamic programming, again, the word programming here is not about computer programming, it's about an optimized way of scheduling or planning, okay? And the word dynamic can be confusing. It really doesn't mean much. It's just about the fact that we consider sub-problems at each step and then build up the entire solution. So that's the idea of dynamic programming. Whenever we have a problem, we want to optimize some sort of objective function. If it's possible to optimize the sub-problems separately and kind of add the results together to optimize the entire problem, that will be when we can use dynamic programming. Questions about this concept? No, actually, that would be a different approach. So the greedy algorithm would be a different approach. I don't want to discuss that here because it distracts people, but yeah, it's a different approach. Okay, now let me just alter the problem just a little bit. Okay, what if we have a certain, let's say, budget of $1,000? Okay, and we know that, for example, a flight ticket is $800. Okay, now we have some sort of constraint there. Okay, now can we optimize the sub-problems here and then claim that we have optimized the entire problem? Can we focus on Montreal to Quebec City and optimize that? Okay, let's just take a flight. They're related. Now that we have introduced a constraint, these two sub-problems are not independent. If I take a flight from Montreal to Quebec City, then I have used up my budget, then it means that I can no longer take a flight from Vancouver to Montreal. Okay, so this is an example of when we have to resort to linear programming, because that's constraint optimization, and it takes care of that automatically for us, which takes us to saying that that's the TA assignment problem. Can we do that using linear programming? Can we assign each TA optimally? Like we give that person any number of courses that that person is enthusiastic about, and then move on to the next TA, and then move on to the next TA. Can we do that? Because of the constraints, basically, right? So the constraints couple the different sub-problems together. Okay. So this is the difference between these cases. We cannot use dynamic programming for that case. And again, whenever I say dynamic programming, meaning that I want to optimize the sub-problems independently so as to obtain a solution for the big problem. Okay. Questions? Okay, so now let's talk about the seam carving problem, and let's see how that relates to this dynamic programming idea. Okay, so suppose that I give you a certain pixel at the top row of this image, somewhere here, okay? I fixed that. You don't need to worry about which pixel we're starting from. And then I want to find the minimum path, the minimum energy path. And what we usually do, let's consider the brute force case. How do we code that brute force case? Yes. Right. Right. So we can implement that recursively because the problem is the same at every. So the rule here is that whenever I have a pixel here, the pixels that I can move to, for example, if I start from this pixel here, the only pixels that I can move to is the one right below that, the one below that and to the left, and the one below that and to the right. These are the only ones that I can go to because I want this seam to be kind of connected. Okay. So if I want to implement that, I start from this. Okay, and then I want to compute the energy. In order to compute the total energy for this path, I have to compute the energy of that, and then whatever comes below that, so a tree like that. Okay, so compute the entire energy along this path, and along this path, and along this path, and that path, and that path. And that'll be the brute force algorithm. And then record the energy values, and then at the end, measure or see which one minimizes that path, right? That would be the brute force approach. Okay, and we know that this will have a time complexity of 3 to the power of n because there's 3 recursive calls. So it will be really, really slow. Okay, now let's see. What if I take this approach? If I claim I'm here at the bottom row, okay, or let's suppose I'm here. Okay, suppose that I'm here. Okay, suppose that I'm here. Okay, and then again, assume that I have given you the path that minimizes the energy from this point onwards, and suppose that it's this path. Okay. Now, if I want to obtain the other partial seam that leads to this seam, what should I do? Can I consider this part of the problem to be done? In other words, does the energy in this seam depend on the energy in the other parts of the seam? No, it doesn't. Okay, so just based on that fact, we can say that this problem is amenable to dynamic programming. So we can start from the bottom and then work our way up. So if we start here, the bottom row, that will be kind of like a base case. The energy at this point is just the energy of this pixel, okay, or the cost of this pixel, we can say cost, okay? And in order, for example, to move up and compute the cost of another pixel here, if I have the cost of these three, then I can compute the cost of this one, okay? So the cost of this one will be the minimum value among these three values. So I have kind of optimized this little problem there, right? I can say that, okay, if the value here, let's say this one is 2, this one is 1, this one is 0, and this is 3, I know for sure that this path over here, 3 plus 2, that will be the minimum energy for getting from here to here. So I kind of optimized that little problem there. Okay. 3 and 2, this, yeah, the maximum. Oh, we want to minimize, okay, yeah, we want to minimize the energy, so in that case, that would be 3 and 0. Yeah. So in this, it doesn't really matter, maximize or minimize. Yes, yes, there are two different ways that we can do this, and actually in the lab, we don't do it this way, we do it from the top down, but I'll discuss that later because this is easier to understand. Okay, so now that I have, if I go ahead and solve this problem, so I have up to, the energies of these are just the pixel values themselves, and now because I have that bottom row, I can compute the energy, the minimum energies here as well, okay? And then when I have the energies here, I can compute the energies here, and at each step, I can minimize that path, right? Okay, any questions about this? It's important for you to understand this, otherwise, I mean, this is the whole idea of dynamic programming. Yes? Oh, yeah, so in order to see what is the minimum, so we have three possible paths here. Okay, so which one minimizes this one? It's the 3 plus 0 here, right? So by doing that, I completely eliminate this part, right? And then, okay, I for sure computed this part, and then I can do the same thing here, here, and here, and here, and then I can move one layer up. Because if I want to consider this layer, for example, I have everything here and here, I can compute the minimum and go up again. And I eliminate all of those options that don't give us a minimized version of the energy function, okay? And again, because these minimum values do not depend on whatever comes above that, that's dynamic programming. We can separately focus on those smaller bits and optimize them and work our way up. Can we do that from the top here? Can I say, for example, if I have 1 here, I have 0 here, I have 5 here, and 3 here, can I say that this is the minimum path? No, we can't do that because this, the path leading from here to here, it's still uncomputed, so I don't really know what happens at this point. Yes? Yes. No, I do compute them, but okay, I was getting at that point. So I do have to compute all of those possibilities in order to be able to compute the minimum, that's right, but the thing here about dynamic programming is that dynamic programming almost, with this top-down approach, always is used with caching and memoization in conjunction with those techniques. So whenever we compute a minimum here, I cache that result, and whenever I have to refer back to that pixel value or that, for example, if I come back to this pixel again from another pixel, I know that the minimum value here is something that I have already computed and cached. I don't need to go down the tree again. So I make each function call only once. Yes? Yeah, we will look at every single pixel here. Yeah. Yeah, yeah. So the idea again is we do that optimization, but if we don't cache the results, then we will come back at the same pixel from various different paths, and that defeats the whole purpose. Yeah. So dynamic programming usually is used in conjunction with memoization or caching. Okay. All right. Yeah. So yeah. Okay. So again, it's because of the way that recursion works, basically. Yeah. I cannot claim that this is the minimum path from here to here just because this stores the minimum value over here. It's different here because, because of the recursion tree, I don't know anything from these points, okay? And if I do this, I don't know if these pixels would have resulted in a more minimized path. That's basically because of how the recursion tree works. Yeah. Pardon me? To the one, yeah, because I fixed that one. And that's the reason that in one part of the code, I actually looped through all of the first pixel rows. That's why. Yes, it has to do that it has to do this kind of same recursion tree for all of the pixels in the top row. And that's a separate step. That's a separate step. Yeah. Okay. Yeah. 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 So we have this condition that, for example, if we are considering, let's say, this pixel over here, in order to compute the minimum path, we can only look at either this one, or that one. Yeah, for all. Yeah. Sure. It's kind of similar to that. Yes, that's right. Yeah. Mm-hmm. We have to run that operation for all of the pixels. What we have computed so far is that if we are at this pixel, we know the minimum path from this pixel to the bottom of the tree. That's what we have figured out. If we land on this pixel for some reason, we know that from this pixel onwards, we have everything we need to know. You don't have to recompute this is so messy. We don't have to recompute this subtree. That's the whole point of it. Yes. Yeah. Sure. That's right. That's exactly right. Yeah, exactly. Because we have to repeat the same thing for all of the top row pixels. Sure. Yeah. Okay. So let's stop here and take a break, and let's resume in 4 or 5 minutes. All right, we're back. We're back. Okay, so I just wanted to show you the code that I have given you here in the lab, and let's just have a look at that. So, okay, so this is the find vertical seam function that here I claim that this is the brute force way to do this. Okay, and you can see here the recursive call, computing the minimum value from all the pixels beneath each pixel that computes the path for us and returns the path for us based on the cost. And I say this is brute force, and what's the reason for that? Because this is exactly what I just described, and I claim that this is not brute force. Again, yeah, sure. Yeah, okay. So this is the recursive function that I have given to you, and it actually implements this approach that I have just discussed. And I said that this is going to be much more efficient. I'm doing the same thing. This is going to be much more efficient. But why do I say this is brute force? Yes. Yeah. So we're still calculating all possibilities, but the thing is, the important element of dynamic programming. Yes. Exactly, we don't cache the results. That's why. Yeah. We actually implement the idea, but we don't cache the results. Okay, so now let's move on to the method that we implement for the dynamic programming case. So what I've shown you is a way of implementing this dynamic programming problem. Another way of implementing this would be, instead of starting from the bottom and working our way up, we start from the top and work our way down. Okay, so it's exactly goes back to the question that you asked, why we have to start from here instead of here, because when we were here, we didn't know what other paths were incoming to that pixel so as to compute the minimum. No, it's not like that. It would be just the reverse case of the same recursion tree, but computing from the bottom. No, it won't be that. Yeah. So the other approach, again, instead of doing this recursively, we start from the top. Okay. I have all the pixel values. All right. So now, in order to minimize the path, I actually look at all the paths and compute the minimum values cumulatively. So I look, for example, at this pixel. I know the energies here. No questions here. This is already optimized. Okay. Now looking at the second row, if I look at this pixel, okay, I know all the paths incoming to that pixel, so I can take the minimum and update this thing here and save it in another matrix. I can do the same thing here, do the same thing here, and update the whole second row. Okay. And now when I do that, I actually have all the energies leading into those pixels, and I can just simply see what the minimum value is there, right? Okay, and we're not done. We go to the next row. Again, we know all the incoming paths, so we can compute the minimum energies and do this again and again and again until we reach the bottom, because this is done in a cumulative way in the lab. When at the bottom we have a pixel saying, for example, 5 or 10, and all other values are like 100, 200, we know that, okay, by following the path that led to that pixel, we can find the lowest energy C, because the cumulative sum of all of the energies led to that value of 10, for example. I know it's a lot to digest right now, but this is how dynamic programming in general is. It takes a while to get used to this way of looking at problems in this manner. It doesn't come like the most natural way in the world to us. Okay. So, questions about this approach? Does it make sense that we start at the top row, we have all of the values, and then we work our way down? Do you know what it's similar to? It's similar to the Fibonacci sequence code that I showed you. So instead of doing that recursively, I start from the value 0, okay, and value 1, those are given, and then to compute the third value, I just use those two, update the matrix. Compute the fourth value, use the two values before that, and update the matrix. And we go work our way up to the value that we're looking for. It's exactly the same approach. This is why I said that is a dynamic programming case rather than the other thing. Yes? 1, 2. 1, 2. Yeah. Exactly. Oh, so yeah. So the space complexity is going to be governed by the cache size. How many different function calls am I going to make to this particular function that I have here? Yes, it does depend on the height. Yeah. Yeah. If we're having kind of sequential arguments to those functions, to be exact. But it doesn't affect the complexity. So yeah, it scales with the height of the tree. Yeah. Any other questions? Yes? For this approach? So for this approach, I can say that, okay, we're looking at this one, we compute everything. Yes, that would be it. Yeah. Okay, we still have m levels, and then we do this thing for, yes. It will be yeah, I think so. It will be different in the constant terms, I guess, because of this is a triangular tree. But I guess, yes, the time complexity, yeah, it will be the same, actually. Okay. All right, so let me just run through the code that I have here and just show you a few results before moving on to the next section. But this is basically it for the dynamic programming. Again, it's not to necessarily make you like an expert in dynamic programming algorithms. No, it's just to give you the right frame of mind to say that, okay, if I have a problem that I can break down into sub-problems and I can optimize each part, this will be a dynamic programming case, and I can go look at a couple of practice problems to see how that goes and refresh my memory. So that's the purpose here. Okay, so this code that we are given in the lab actually implements this way, not the other one. And let me just run this and show you a couple of results. This is the energy of the image that we have, or a smaller image basically, but this is the energy of the pixels, and the smaller values correspond to less important pixels. Okay. So if I do find the vertical seam here, it's telling me that in this row the vertical seam corresponds to this one, and then to this one again, and then to this one, and from that one again, and then finally 2 over here. So it's a path like a 4, 4, 1, 3, 2. Okay, let's see how that works progressively. Okay, I create a matrix called cumulative minimum energy, CME, and basically in the beginning it just stores the energy values, and I'm going to update that as I start from the top and going to the bottom. I'm going to keep updating that with the same approach that I discussed. And don't worry about this infinity values. This is just to not move into the bounds, because those are not going to be the minimum values, so we make sure that we're not stepping on the borders. Okay. So let me show you the first whole row. Okay, 94991, 94991. So this is the same energy image here. This is the same first row. We don't touch that. But for this one, I have actually computed the minimum value of the adjacent cells and then added that to the original pixel value. For example, for this 4, I have looked at all these paths, okay, and I have computed in the original image. So I have looked at 4 and 6, 4 and 4, 4 and 6. So in this case, 4 and 4 would be the minimum value, and you can see that the result is 8 here, okay. So this is where I progressively compute those minimum values and update the matrix right there, because I only care about the minimum values. I don't need to keep track of 2 other things as well. I don't care about that. So I can just get rid of them and store the minimum value here. Okay. And then we do exactly the same thing for all other rows. I take this row again and then look at the possible paths from 10 to infinity, 10 to 1, 10 to 5. The next one would be 10 plus 1 would be 11. So I put an 11 here. Okay. And finally, when we get to the bottom, when we get to the bottom, we will see something like this. Okay, so now the bottom row is telling me that this pixel stores the minimum cumulative energy, right? It means that however we landed on that pixel, that's the path that we should take, right? Because this gave us the minimum sum of energies. And we can do a process called backtracking, meaning that we start from that pixel, we say, hey, where did you come from? You should have come from either this, this, or that, and then we work our way back up to see what exact path we have taken in order to land on that particular pixel. And this is the other approach that I told you. Yeah, the backtracking discusses this. You can, if you're interested in details, you can look at this on your own time. I don't think it's necessary to do this here. This is basically the idea. Okay, so this is the question again. I mentioned this in the beginning rather than in the end, and I hope that this is clear now why we can't use dynamic programming for the TA assignment problem, right? Again, because in the TA assignment problem, if I give all of the enthusiastic courses to the first TA and then give all of the enthusiastic course to the second TA, I can't really do that because of the constraints. So those sub-problems are not decoupled, are not independent. I have to look at all of them together. Okay. Questions before moving on to the next section, and the last section, actually. Yes? Sure. Yeah. Pardon me? Right, yeah. Oh, okay. So yeah, good point. In this case, we actually have two 12s here, meaning that we have two equally good paths leading to that minimum energy C. Yeah, we have basically two optimal solutions in this case. Yeah, we can take either path. Okay, any other questions? This shouldn't be the case. If we take the right path, we land here. If we take that solution, we land here. Are you sure? 12, 10, and then... So yeah, the minimum value should be the same. Can you do this summation? 14 plus 12 plus 10 plus... Oh yeah, you can... Yeah, this is not... Yeah, this is not the actual matrix. This is the cumulative energy matrix. Yeah, right. Yeah. I shouldn't have looked at the cumulative energy. Oh, okay. Sure. So, let me see. I have to pull up this backtracking part. Okay, I have explained everything here. Do we need to go over this right now? Because it takes a while to... Okay, so I have explained everything here in this part, the backtracking part, and I start from that bottom row and then looking at the original table, I say that I should have come from this pixel to land here and should have come from this pixel to land here. This is how it works, but there are a bunch of steps from that. Okay. Yeah, it's tough. Okay. All right, now we're kind of done with this part, and there's actually one last part to the lab, that you implement the same problem using linear programming. And it means that, okay, if we can do the harder cases with linear programming, we can do this particular problem, which is simpler using linear programming too, and you have the constraints in terms of having only one pixel at each row, and that's basically how you can implement that, is using linear programming as well. Okay, but the linear programming case would be a little bit slower compared to this one. The time complexities are actually different. All right, now let's go back to our favorite topic of code vectorization. and let's discuss this a little bit in more detail here, and then finish the topics that we wanted to cover in this course. So, vectorization. I have these two NumPy vectors, and in order to add value of 1 to x and store it in y, I can write a for loop like this, and by this point, we know that this isn't going to be efficient. Okay, I'm going to just time this again, 1.98, 2 seconds, and then I'm going to do this using a vectorized operation, and then, yeah, it's 3 orders of magnitude difference in time. This is 12 milliseconds, the other one is 2 seconds. And by this time, we know that inside of here, so let me ask you a question. Is this because of the time complexity or because of the implementation? Time complexity, why? No. So we're adding a value to all of the elements inside of that vector. We have to do that anyways, so it doesn't change the time complexity. It's actually the implementation. Because, and the reason is that here, when you do that in Python, Python sees that for loop, says, okay, I have to add 1 to this value of x, to that first element of x. Okay, here's your value. And then we go back again and you say, okay, I have to do that again for the second element. I have to do that for the third element, for the fourth element, fifth, and so on and so forth. So each time we do that, we have to make a separate call to the Python interpreter, and it has to compile the code for us, turn it into machine code, return the value to us, and then just relax until the next line of code comes up. However, here, when we do this, we do that inside of like a kind of a package. So when Python sees this, says that, okay, this is a NumPy array, I'm going to do a whole bunch of operations, so let me put my x plus 1 shoes on, and then work on that like entirely, instead of going through that one by one line and elements by element inside of Python. Okay, so this is called vectorization. And again, this is not something that is always the case. For example, if you use a compiled language or other a little bit more sophisticated languages, you can actually get rid of something like this entirely and write your code in the most natural way. So the most natural way would be something like this, at least initially, before getting used to vectorization. For example, there's a language, I don't know if you've heard of it, it's called Julia, which is picking up a lot of popularity for scientific computing. And that's a language that's called, has a feature called just-in-time compilation. And when you write a code like this, it doesn't go through that line by line, and it actually processes bits of code and compiles bits of code all together. It kind of is smart enough to know that that should go together. And you can write your code in every way that you like, and it takes care of those optimizations for you under the hood. So I guess this trend is coming in the future, that we don't have to think about vectorization as much, but right now we have to deal with it for the foreseeable number of years. Okay, so I have an example here, computing pairwise distances between values inside of x and y vector, and we're going to look at that and how we can compute that efficiently using vectorization. All right, so I have two vectors. Each one of them has 100 dimensions or 100 features, and I want to compute the distance between those. We can use the Euclidean distance over here. And the way that we can use vectorized operations is that we just do sum of x minus y raised to the second power, and yeah, sum everything together. And when we write it like that, NumPy knows how to subtract those two vectors from each other in a vectorized way, how to exponentiate the result in a vectorized way, and how to sum that up in a vectorized way. Okay, so everything is super efficient. All right, now instead of having just a single vector, suppose that we have that 100 dimensions, but we have 5 observations for x and 3 observations for y. So this is becoming a little bit more complicated, because in this case, yeah, we have 5 rows and 100 features. So we have to compute 5 by 3 distance pairs, 15 pairs in this case. And yeah, the way that we can do this, the more the simplest way is by writing the for loop like that. So go through each and every row of x and compute the pairwise distance with all of the elements inside of y, right? Take the first one, compute the pairwise distance. Take the second one, compute the pairwise distances. Okay, but that's not super efficient. So here I have the same code wrapped inside of a function in order to be able to time this. And let's look at square distances. Yeah, let's use a bigger value for the number of rows and time this. It takes quite a bit of time, and this is not a very large data set kind of thing. So 3.9 seconds. Oh, I gave away the answer. So the running time of this pairwise square distances is going to be the number of features that you have, because you have to loop through them, and also the number of rows inside of x and number of rows inside of y. And that's because we have to look at everything. Okay, so d and x and y. Okay. However, we can do this in a more efficient way. We can implement this code over here in a more efficient way. And basically, we can use the concept of broadcasting that I brought up in 5.11. So in 5.11, when we had a suppose that we had a vector like this filled with values, and we had a vector containing a single value like that, instead of like going and creating a for loop to compute the distances between these, what we did was that we simply do, for example, if this is x and this is y, we simply did x minus y, right? And in that case, Python, NumPy was smart enough to know that it has to copy these elements here in order for that operation to be feasible, right? So it created this kind of copies of these values of this element in order to be able to do that operation efficiently for us. And if you actually try this, looping through this compared to doing this like that would be much more faster in that case, because it uses broadcasting. And this is essentially what we're planning to do here with this case. Instead of using this for loop, we can do broadcasting. So let's see how. Okay, so here a 5x1 vector, just as an example, and here I have a row vector, and in order to compute something like xx minus yy, yeah, either I have to copy those elements here or copy these elements here manually, or I have to do a for loop, which I don't like to do. And Python automatically knows this and broadcasts the two vectors together so that this operation is possible. And this is very efficient. And this is what I'm really interested in implementing. Okay. This is the shape of our original x's and y's. So can we do broadcasting in this case? If you remember from 5.11. We had to start from the right-hand side and check the dimensions, right? So 100, 100, that's good. 3 and 5 doesn't work. Okay. So we have to create extra dimension here in both of the matrices in order to be able to do that operation. So if I do something like that and add one extra dimension here in the middle and do something similar with the y and add an extra dimension here at the beginning, now this broadcasting would be possible. 100, 100, 1 and 3, 1 and 5. That would be possible to do. So when I do that, the result will be something like this, and I can rewrite my function in a very concise syntax like this, which is actually completely vectorized. Okay. All right, let's now time it again. So this is the original pairwise square distances. Takes a while. This is using broadcasting, way faster. Okay, and this is something that you will do in the lab. So you have the dynamic programming case, and you will try to write a vectorized form of that dynamic programming in the last part of the lab. All right. Yeah, we're not going to cover this. If you do the same kind of pairwise distances operations using scikit-learn, you'll actually get a much bigger jump in the time efficiency. So instead of 300 milliseconds, it actually computes it in 10 milliseconds. And that's a huge factor of 30. And that's because under the hood, it uses some mathematical transformations in order to make this operation faster. So instead of doing the sum like this, squared sum, it turns it into a bunch of matrix multiplications. And matrix multiplications are super, super efficient. And I don't know if you've heard actually, so lately the company Alpha Tensor came up with a way of multiplying matrices together even faster than before using AI. So they found patterns in the way that you multiply those rows and columns together that actually computes the multiplication and is actually faster. So it does it in fewer number of operations. That's not too important here. Okay. Yeah, so some text here for you to read through, basically some guidelines. And there are a bunch of other stuff here that we're probably not going to talk about that much. But let me just tell you what's following. So here, I have a bunch of sections, profiling, for example, parallelization of code and other tools to speed up Python code, and also one other really cool example of dynamic programming. So the thing that you see in GitHub, or not in GitHub. So you see something like this for the diffs, and there's quite a lot of details to this, but this actually uses dynamic programming in order to efficiently compute or obtain the differences between two pieces of text, which is crucial in GitHub. That's something that we use probably every day. And yeah, the code is here, explanations are all there. You can look at that in your own time. This is an interesting example. Other than that, let me also just walk you through, just briefly discuss these other items that we have here. So before that, any questions about vectorization, this section particularly? So basically, it comes down to being able to translate things into NumPy's language so that we don't have to write a for loop. The trade-off is that a code like this is not really as readable as doing the for loop. That's the trade-off. It's really hard to understand what exactly I'm doing here, what type of data is stored in. Type of data are stored in X and Y. So, but if you want to have efficient code in Python, we have to be willing to accept that trade-off. So it would be nice in this case if other languages like Julia become more popular and we can write code in the most intuitive way possible. All right. So we have a couple of minutes left. So I have a tool here for you to profile your code. And what this does is that when you have a piece of code and you want to run it, you don't have to really go and look at every line of code to find out what is the bottleneck for the performance. There are tools that do that for you. Here we have a tool called Snake Visualization, and it basically gives you a whole summary of what's going on in terms of execution time for different parts and different lines of your code. And you can look at that, rank the results, and see, this is the line that's taking too much time. So I can probably do something with it. That's profiling. And yeah, another option for enhancing the performance of code is actually by doing parallelization. So instead of running everything on one processor, you can distribute your job over multiple cores of CPU or multiple processors. This can only be done in cases when the things that you're doing on each processor do not depend on each other. If you're, for example, having a for loop, you're computing something from the previous step that is necessary for your next step, you can't really parallelize that on CPU cores. But in case that those steps are kind of decoupled from each other, then you can distribute the job and then aggregate the results in the end. That's also an option in Python, and it actually can be really, really useful. It has helped me in the past. So, for example, decreasing the runtime of my code by a factor of 5 or 6 by running the code on my CPU cores, for example. And I have given you the code that does that. You can read through that as well. And okay, let me show you this other cool example of how you can speed up code. Right. So one thing that you can do in order to speed up code is that if you run this code, this is a simple for loop. It takes a lot of time, okay, obviously. However, there is this package called numba, which whenever you add it as a decorator to your function, it sees that function in its entirety and tries to compile the whole code at once. So it sees that function, the for loop, whatever's inside it, and then turns it entirely to machine code. And then when it does that, you don't suffer from the same performance bottleneck again from the for loop. So if you do this, I haven't imported the package here probably. No, joblib. Yeah, when you do that, it compiles the whole thing together and then makes it much, much faster. Okay, yeah, that's here. All right. Go back here, so it take 1.73 seconds. If I do that and then run the timing again, 154 milliseconds. So this is another nice tool that you can use if you want to do that, if you are eager on running the code in a compiled way on Python. This is a nice tool. And other than that, I guess, yeah, the rest of it is not that important. All right, so the course wrap-up. Breathe. Okay. All right. So, in this course, we've learned about analyzing code to see how many steps it takes to run a certain piece of code as the code scales. So if I have a data set that's small right now, what if I scale my data set? What is the expectation? Will I be ever able to run my code on my computer? Will I be ever able to run my code at all? So right now we know that, okay, if you have recursive functions, we have to be careful about exponential times. If we have a data set that's sorted, we don't have to do linear search because it's sorted, we can eliminate a lot of possibilities. We also learned a lot about specialized data structures. So what is a graph used for? What is a list used for? What is a dictionary used for? So we just see the dictionary object in Python. How is it implemented under the hood, and why is it fast for insertion and lookup, and how can we use it efficiently for our purposes? And we also talked a little bit about optimization in the last two lectures, and also just a few ways to speed up your code, but mostly we discussed algorithms and data structure. And this list is not exhaustive. We discussed a bunch of other things as well. So point here is that this is not a full undergrad course that takes 3 to 4 months. We didn't cover a lot of things that you probably see in other places, different algorithms for searching, sorting, stuff like that, and a bunch of other topics. But the goal here, just to emphasize that once again for the last time, is that the purpose was not to make you an expert in algorithms and data structures. It was to give you the right frame of mind to start thinking in an algorithmic way and start recognizing patterns in your code if you see performance issues, and start thinking about algorithms in a more systematic way and the right choice of data structures and implications of those data structures. We will see, for example, in your database course 2 weeks from now, that these things we will encounter all of these concepts again and again. So you run code, you query a database, the thing is slow. I can then immediately tell you, oh, this is because this operation is going to be n squared when this is not sorted. So we have the right way of thinking about these kinds of topics. So I hope this was helpful for you, and I enjoyed very much doing this course, working through this course with you. And I'll see you in the lab and next week in the quiz. Thank you so much for all your efforts. Thank you. Thank you. Hello.